with that, we're going to move on to the next presentation on dynamic control building load for emission reductions. Again, another topic that ties in very well with everything we've been hearing these 2 days already. And Henry Richardson, he's an analyst for WattTime, and at WattTime, they try to understand and work with the effective electric grid and achieve the greatest reductions in greenhouse gas emissions. So Henry, his background, he specializes in emission-focused load shifting, energy storage integration, and methods for assessing overall building emissions. So with that, I'm going to pass it over to Henry, and welcome.
Hi, Ted. Thank you for the introduction. I'm going to quickly share my screen here for the presentation and get rolling. This is a little bit of shifting gears, I think, from really building focused content and to expand the view a little bit wider to the electric grid and how it interacts with emissions in the buildings. And so I'm going to kind of quickly get started, a quick introduction on WattTime, and then lay a foundation for everyone on understanding the electric grid and how it works, and then bringing that information to how can buildings respond to grid signals and change their load to reduce emissions, and then kind of a discussion at the end of like where we're seeing this going and how different folks are starting to create dynamic response to different grid signals. Feel free to jump in at any time with any questions, raise a hand, and I think we can unmute you or put a question in the Q&A.
Yeah, we put them in the Q&A area.
Excellent. Let me just put this in full screen mode if that works, so that we lose some of the other stuff. So here's the obligatory slide, but WattTime is a nonprofit that's really focused on giving people the ability to choose where their electricity comes from. So what that really entails is we do a lot of deep dive in understanding how the electric grid works, and then bringing that information into decision-making around renewable siting, dynamic load control, and various other ways we can apply this data. And so we're a pretty small nonprofit, only about 30 working on some interesting projects. But first I want to kind of do a deep dive on understanding the electric grid. So you actually can somewhat choose where your power comes from. The grid is a mix of a whole variety of different resources, and at certain times there's an oversupply of wind or solar. Then if you operate your device, you'll be able to use that. At other times you'll be pulling power from dirty resources like natural gas or coal, and we really want to enable that choice through kind of automated control of various devices. And this is, of course, a really simplified view. This begins to make it a little bit more complex. And you may not be familiar with this particular chart, but it's a dispatch curve or a dispatch stack. And each of these bars represents a different generating resource in that grid region. And they're arranged by the width of the bar indicates how much power that resource can provide. And the height of that bar indicates the price at which they will produce that power. So some renewables actually bid negative prices because they have other revenue streams like tax credits or RECs. And then all of these other generators bid like, oh, to produce power, this hydro plant must receive at least this much money. And so for a given demand level, let's say everyone in the state is using 30 gigawatts of power. That means every power plant to the left of this must be operating to provide power. And so you can start to see that, oh, first they turn on the cheap and often clean things, then they turn on the other resources. Then as you get towards the peak, they turn on those really dirty, expensive resources. And as demand shifts, you can start to see that the responding resource changes. So for example, at this time, if you increase demand, a natural gas power plant will ramp up to meet that demand. At this time, if you increase demand, it'll be a coal plant. And this mix of available resources is constantly changing throughout the day. Like the solar is not available at certain times, whereas the wind is available at others. And so you can start to see that like we rely on different resources at different times. And sometimes there's an oversupply of wind and solar that we can really take advantage of. And so this is kind of a simplified view of how the grid works, and we really care about what that marginal resource is. So if you have an EV and you want to plug it in, you can say, if I plug in my EV right now, will a wind farm throw away less electricity, or will a gas plant ramp up to meet that demand? And that's the question we're always trying to answer. And you can start to begin to see how this might affect building building load flexibility, or building load scheduling. Of course, this simplified view is great, but we use a much more complex empirical model that looks at all the different changes of demand and resources and the emissions of actual power plants available from the EPA. We combine that with grid information from the ISOs and balancing authorities, and those are the entities that actually control the grid and determine which power plants turn on and off to identify that marginal resource. So we can answer at any given time which power plant is responding to that change in load. And you start to get charts like this, where you say, oh, there's an oversupply of wind at this time at 3 a.m. That's a better time to be consuming electricity. We want to avoid these dirty times. And then there's also an oversupply of solar here. So you can start to see there are kind of actions and activities that might be advantageous. And then WattTime has built a whole infrastructure to support this. So we take a bunch of real-time and historical grid data. We ingest that from a bunch of different sources. We run it through our algorithms to determine that marginal resource. We build a 72-hour forecast, and then we push that information to a bunch of data partners who then ingest that information and act on it. So in this case, building controls are the probably most relevant, but we work with, smart thermostats, EV charging and EVs directly, appliances, hot water heating, smart compute load. Can you shift when you run a specific compute load? And so you can start to see there are a bunch of different loads that could respond to a carbon signal. We're excited about thermal storage. UC Merced has an enormous thermal storage tank that can be charged at different times based on a carbon signal. Pumping for agriculture can also be dynamically adjusted based on load signals. So you can start to see this touches a lot of different industries. I'm gonna talk through some kind of like how we visualize and think about this, but any questions on the grid related stuff before I move on?
No, there weren't any yet.
Great. So a really super simple example is like, if this is the marginal emissions rate, there's a lot of excess solar in the middle of the day, can you change your compressor cycle timing to align with those low emissions periods? What kind of tweaks can you make in a building? Can you adjust the set points? Do you have direct control of the motors on those compressors? What kind of ways can you touch the building? We also see this with electric vehicles. They're kind of a really intuitive, easy to understand example. So you come home, you plug in your EV, you don't really need it until 8 a.m. the next day. So under a traditional control, that EV would just start charging immediately to fill it back up. But with kind of this kind of dynamic emissions control, you can take that forecast and say, okay, we have this window that starts at 6 p.m. and ends at 8 a.m. What is the cleanest period in that window, and can we selectively charge during that period? You can see that the EV, this is a real world example in partnership with NLX's JuiceNet Green, where there was a little bit of initial charge to provide a minimum and to understand the level of the EV. There was a quick drop, so there was a little bit of charging, not much, and then the control algorithm saw a significant drop in emissions and said, okay, now's a great time to charge, fill up as much as possible. And then when the spike occurred, it actually stopped charging and then started charging again after that spike decline. And you can see there was a nearly 90% reduction in emissions because of instead of relying on those peaking natural gas power plants to provide power to the EV, it relied more on the excess renewable energy in the wind. And you can see the same approach in energy storage, where you want to align the charging and discharging of the energy storage to take advantage of that emissions differential. So you charge during the low emissions periods, and then discharge during the high emissions periods. We're starting to see a lot more energy storage appear in commercial buildings. Traditionally, it's been targeted for demand charge reduction, but we're starting to see some energy arbitrage and some emissions specific dispatch. And so the orange line here is the charging and discharging rate, and then the dark blue line is the marginal emissions rate. And you can start to see they're beginning to align, where they're discharging during those peaks and charging during the lower emissions periods. And you're really trying to take advantage of that emissions differential to the largest degree possible. And then one of the kind of probably most relevant examples we've seen is we're partnering with an organization called Brainbox to really start to think about what does it look like to take emissions-aware control into buildings and actually dynamically control them. And so what our partnership with them is, we are the signal provider. We understand the emissions intensity of the grid. We take that real-time value in the forecast and provide it to them through an API. They ingest that information, and they install, I think, both hardware and software in the building to be able to zonally control and control all the equipment. So we're the signal layer, they're the control layer, and they actually say, okay, we see that this is the kind of forecasted emissions throughout the day. Can we pre-cool that building or preheat that building based on that signal so that we can kind of capture those low emissions periods? And if I understand correctly, they're actually going in and adjusting set points to a small degree so that the occupants don't see that change, don't necessarily detect or feel that change in temperature, but then the compressors and the other chillers and all the equipment in the building actually is responding to that change in set points so that their operation is shifted around in time to better align with the low emissions periods. And then the system, of course, learns the tolerances of the building, how much thermal lag it might have or thermal mass, things like that. So that kind of, like, you can start to see that this is a shift away from set it and forget it and towards much more dynamic control of, like, every day, can we change the operations of that building and think about how we can control when that building operates. And it starts to get into complex questions around, in addition to making sure the building, instead of just thinking about it from a monitoring standpoint and making sure the building is operating properly, there begins to be a feedback loop around, okay, we're actually going to dynamically update the equipment in the building and when it operates. And that's a much more sophisticated control system overall. Those are kind of the key steps I wanted to touch on there. There are a whole range of different technologies that you could potentially control in a building. So we kind of touched on preheating and pre-cooling. That's adjusting set points. We're seeing an increasing number of buildings considering thermal energy storage, not just battery storage. So either ice storage or chilled or hot water, sometimes both in the same tank. We've started to hear Train talk about that. And so that really gives you the ability to, thermal storage really gives you the ability to kind of increase thermal lag and run those chillers at more optimal times. We ran a study in partnerships with LBL at UC Merced with their very large thermal tank, where they built a model predictive control algorithm that actually charged that tank based on both the price signal that the university was getting, as well as the carbon signal, to dynamically kind of select between them. And prior to that, there was actually, by incorporating a carbon signal, there was a significant change in chiller operation without a significant effect on utility costs, just because TOU rates are undifferentiated. So you can kind of charge anywhere within a TOU window without affecting cost. but there may be better or worse carbon times. Battery storage is probably the purest form of electricity arbitrage. You can charge and discharge at different times and really take advantage of that differential in emissions. Different jurisdictions have all the different kinds of rules around how energy storage can be integrated into buildings, but we're definitely seeing a significant increase. Another one is sensors and lighting controls, for lighting controls. I think we typically see this as more appropriate for demand response, and we'll get into why that is. But if you can reduce the lighting levels at a given time, is there a reason you aren't doing that all the time? It might be good for critical peak periods when you want to reduce lighting, but overall, I have questions around how to use lighting as a kind of dynamic load control operation. Hot water heating is obviously another good place because you usually typically have some form of built-in thermal energy storage. If you put a mixing valve on that tank, you can overheat it potentially, and then mix in cold water. So it becomes a really dynamic and much longer range load flexibility asset in the building, especially if you oversize that tank when you're installing it. And then it becomes a question of, okay, how do we plug into the control of that smart hot water heater? And then kind of a new area that we're starting to see more interest in is plug load management. Are there non-critical loads? Can you connect to things that already have some kind of flexibility? There are obvious ways to control, like when the building is unoccupied, but when the building is occupied, do you know if you're connected to a laptop? Can you actually turn off that laptop for dirty periods and then essentially forcing it to recharge during cleaner periods? So that's kind of there are some links here at the bottom to different resources that talk about different load flexibility strategies that can respond to carbon signals. I do also want to quickly touch on there's a lot of language that is used to describe these things. So load flexibility or demand flexibility you'll often hear in response to different types of signal, whether that's a price signal or a carbon signal. We've heard the term environmental demand response to describe, instead of responding to a price signal, you're responding to a carbon signal. GEBs, or grid interactive efficient buildings, this is often used by the DOE to describe buildings that are dynamically controlling their load, specifically to a carbon signal, specifically to a grid signal of some kind. We at WattTime often use the term automated emissions reduction. So there's an implied level of control, whether that's automated emissions reduction in a building, in a device, in an appliance, in an EV. It covers a lot of realms. Carbon-aware load control or carbon-aware dispatch is used often in the tech industry to describe dynamic load control for smart compute load. And then real-time pricing, dynamic rates, that's a kind of a term used to describe a move away from static rates and TOU signals. And so these are all the types of ways that load flexibility are often talked about in this world. And then finally, I want to quickly touch on a paradigm shift away that we're starting to hear away from traditional demand response towards continuous demand management. And it's requiring a kind of a pretty significant update in how people think about buildings. So traditional demand response is really focused on a very few peak events throughout the year where the utility or grid operator calls like, hey, now's a critical period for you to reduce load. Please go about doing that. And that may be automated. It could even be manual. We often hear the term sneaker net, where like someone who literally walks across a building and turns off certain circuits. And we're moving towards a system of continuous demand management where it's dynamic and responds to a changing signal. And that requires kind of a greater level of sophistication in the building operators, where they have to make sure that those systems are connected, they're working, they're controlling the right things and achieving load reductions at the right times and corresponding load increases at other times. And And so that's definitely an interesting industry update that we're seeing is growing significantly. That was really all the pieces I wanted to touch on. Any questions from anyone or anything we wanted to discuss here?
Yeah, I just have a little bit of a thought in this relative to the technologies involved with this. Um, how far off are they to be able to have this commercially integrated? And in particular, I'm kind of thinking in lines of, well, if I have my house, I'm looking at installing a heat pump water heater. I'm going to be installing solar, kind of considering looking at a battery backup. But with all these different aspects of the grid and looking at when the grid is greener than other times, the cost to do that is basically at this point borne by the homeowner, right? And I don't see the structure in the utility rates to help promote this. And some of that's got to do with the actual cost, and that's why I started out with the cost aspect of it. What do you see happening in that arena? And maybe it's a little bit outside of your talk, but I just thought I'd ask.
Oh, definitely. So there are a bunch of really interesting developments around this right now. So there are some existing dynamic rates, especially I believe in Oklahoma, where the rate varies significantly over time. We're starting to see the kind of push towards that in California as well, with the CEC and the CPUC putting forward proposals for dynamic rates or requiring that the utilities provide dynamic rates. But we're also seeing a lot of voluntary uptake of the ability to optimize for a carbon signal. So for example, the Nest Renew program, it doesn't affect your utility bill, but it does really help drive emissions reductions, where you can opt into a program that controls your thermostat based on a carbon signal, and it will adjust your use based on that carbon signal. We're really seeing a lot of this in EVs because they're such a large load and can be so carefully controlled. And we're seeing consumers are pretty excited about this, just because just like people opt into, like, your utility probably provides a program that lets you buy clean electrons, theoretically. We can talk about the reality of that, but this is another way for consumers to actually act on that carbon signal at no cost. If you're on a TOU rate, you can still charge in the off-peak period. You're just charging at a different time in the off-peak period, so it doesn't affect your revenue, but you still have an environment.
Okay.
Does that begin to answer your question?
Yeah, it does. I'm gonna just put out one more question, and then we'll move on to the next speaker. An operating engineer is typically, Michael Bobker is asking this question. An operating engineer is typically looking at his or her equipment doing certain things at different times, or certain times. When that changes, as you suggest, an operator may become concerned and go to manual override. Is this something you have thought about how to overcome? In other words, a building operator will run the building according to their level of understanding, right?
Absolutely. And I think we see that the building engineers, the people in the operating engineers in the building, are a key part of, like, understanding. You can't just implement this. You need them to be the people implementing it, understanding why the compressors are running earlier or later, or seeing those set point changes. And we also have to make sure that their occupants in that building are not unhappy with those changes. So it's a very integrated process where we see the building engineers or the operating engineers as part of that chain of people that understand how this is working. Michael, does that begin to answer your question?
He can't unmute, unfortunately.
Yeah.
So, well, Henry, thank you very much. Good presentation, good data tying into a lot of the presentations already given past 2 days here. Thank you. And we're going to move on.